So we're just going to evaluate this, a little bit of order of operation stuff, a little bit. But what I notice is that we have a minus and negative right here. And I don't like to see that garbage, so I'm going to make that just a plus sign right there. In fact, you could do it with the plus the negative 8 there at the end and just make that a minus sign also if you wanted to. That's really up to you. We're in 9th grade, so you could just plug it into a calculator if you want to, but you don't have to. So if I was evaluating this, negative 9 plus 5 would be negative 4, and then negative 4 plus 3 would be negative 1, and then negative 1 minus 8 would be negative 9. That would be our final answer. So a quick note on math, because we're going to be doing this kind of stuff a lot in 9th grade. You probably did a lot of it in 8th grade and 7th grade, probably without knowing, but sometimes math is just kind of what we want it to be. It's what we want it to be, and then we can force it to do what we want it to do, as long as we don't change values, okay? So what I'm talking about is, let's take a unique number like the number 1, which doesn't seem that unique. But 1 can be pretty much whatever you want it to be, depending on really what you want it to be or what you need it to be. So if for some reason you need 1 to be 16 over 16, you could. You don't have to write it as 1. You can change it so that it looks different, but you see also that it has not changed the value. You could also write it as, I don't know, 14, well, I guess divided by 14 if you wanted to, something like this. Or you could write it as 1 times 1 if you wanted to. You could make it 1 times some kind of fraction again, like 15 over 50. I don't know, these are just kind of random examples for one. But the truth is you can kind of force some of the things to be what you want them to be. In fact, usually when we look at simplifying expressions, kind of like we did on the bell work, how if you see something like this one, I know it's not exact, but if you saw something like this, if you see a minus and negative, you're welcome to just make that a big plus sign and then just change that into 5 plus 4. It is exactly the same. The result is exactly the same. But you're just showing it different because maybe it helps you to understand it better. But you're forcing it to do what you want it to do, and you're not allowing it to take control of your life, because when math takes control of lives, it tends to destroy them. So here's our objectives. I can use the distributive property, and also I can combine like terms. So this is our first lesson. You have the worksheet. It says objective on there. This is where you write the objective. So I'll give you 60 seconds to write these two down. Then we'll get started with the rest of the lesson. Hopefully you notice that these two objectives are things, hopefully, that you've heard before and have done a little bit of, at least. So hopefully you remember doing this stuff, because you did a lot of it in 8th grade, and then probably a lot of it in 7th grade as well. So this lesson is really just a review to help us to get along with some other things that we're going to be going over in this unit, which is just solving equations, which we'll be doing next time. So first off, we got to go through some vocabulary, like variables. Variables are usually represented with letters. We usually use X in this class for math. We don't always use X, but most of the time we do. When you're going to use your own variables, it's usually wise to avoid O's, I's, L's, at least lowercase i's and L's, and lowercase e's. There's reasons for that, but they're all nerdy, so I kind of assume you don't want to hear them. Now, variables, yeah, sometimes they can represent many values if you're just kind of creating your own formula for something. But when we see them in the equations we're going to be doing, for the most part in this unit, they will represent just one individual value that would make the equals statement a true statement. So using and defining variables is a key feature in problem solving, sure. All right, so terms. Like terms, coefficients, and constants. I use this vocabulary quite often. Not just in this unit, but in almost every unit that we're going to be going over in this class throughout the whole year. So if I say term, it's important that you understand what I'm talking about. If I say coefficient, it's important you understand what I'm talking about. So a term is just a value in a math expression that's separated by addition or subtraction. Sometimes it may look like there's lots of terms in an individual term, but there's just one. So sometimes when students see something like this, they say, there's two terms right there. There's not, it's just one. Because they're separated by addition or subtraction. This is multiplication between the 4 and the x. So this is its own individual term. Sometimes a term may look just like this, -8. And that's fine too. It by itself can be its own term. Now usually there's other terms that go along with it, which we will see. But if we ever see like terms, what we call like terms, then we can say that we can combine those terms. But like terms generally have, well, sometimes they don't have variables, but if they do have variables, then the exponents of those variables have to match in order to be considered like terms. So, for example, that 4x up there that I haven't read, if I looked at something like 5x to the power of 2, this 5x to the power of 2 and the 4x are not like terms because this x has a power of 2 and this x does not. So they would not be like terms. Now, theoretically, if I were to take that 2 away, that power of 2, now we would say that the 4x and the 5x there are now like terms, and I could combine them to get one final sum of x's. It'd be 9x's, of course. So be aware of that because I believe we're going to see some of that today when we're combining like terms, whether it's on the assignment or on the classwork. Now, a coefficient is just a number that's being multiplied by the letter. It says base numbers of a term. It does take the operation to its left as its sign, whether it's addition or subtraction. I didn't mention this before, but terms do the same thing. So a coefficient is a number being multiplied by a letter or a variable. So if I looked at this term right here, the 5 is the coefficient because it's being multiplied by the x. If I look at this term right here, 4x, the 4 is the coefficient because it's being multiplied by the x. And the exponent of the variable doesn't matter, so even if I said that was 5x to the power of 3, the 5 is still the coefficient. It's just of an x cubed now. Now, with the -8 up there in red, would that be considered a coefficient? No, it would not, because it's not being multiplied by letter. It is what we call a constant, which is just a number by themselves. That's here at the bottom. So again, I may refer to numbers as constants if they're by themselves. If they're being multiplied by letters, I may refer to them as coefficients. But whether it's a constant or a coefficient with a variable or letter, they can still be their own terms. So these ones I'm going to go over just because they tend to trick students. We're saying, what is the coefficient of x? Remember that a coefficient is a number multiplied by a letter. All right, so that is a coefficient. And some students look at this first one, -x, and they'll say there is no number being multiplied by the letter, but there is. You just can't see it. It's what we call a phantom 1. Okay, now I'm showing it, so it's not a phantom 1 anymore. But I don't have to show it. So just be aware that if you do not see numbers, sometimes they're still there. So that 1 that I just erased, it's now in the shadows, lurking, always watching. Which kind of makes these kind of creepy, right? But the coefficient for this one, it is -1. Well, what about this one? It's 8 minus x. Well, again, there is a number there being multiplied by the x. It's not 8, by the way, because it's 8 minus x. Again, it's a phantom 1. But remember that the coefficient, just like every term, will take the operation to its left as its sign. So it's not just 1. This one is a -1 also. Okay, so this last one, hopefully we get the idea. There is a phantom 1 right there. The term itself is just 1x, but the coefficient is just the 1. So expect to see those because it'll be important for us to know that those 1s are there when we start looking to combine like terms and also to distribute. So here's a big expression. Kind of ugly too, right? Because it's so big. Now, like we talked about before, sometimes math is just making things be what you want it to be. Well, I don't want this to be this big, okay? So I'm gonna narrow it down so that there's only 3 terms. Why is there only 3? Because there's only 3 types of terms in this math expression. I see I have x terms, which are just terms with just x's. We have a coefficient with x. We have constants, so that's another type of term in this expression. And then we have x squared terms, x to the power of 2 terms. And those are, if you scan through this, you'll see that that's all the types of terms there are. So I want to, well, maybe not want, but I'm going to force this to be 3 separate terms. And I know I cannot combine them because those 3 different types of terms are not like terms. So I do have to keep them separated in the end. And it does say to simplify, but let's identify the terms, okay? So I'm going to start here with the 5x. So I know that I am expecting x terms. So let's list them. All right, so again, just right off the bat there, I've already listed or underlined the 5x. So the 5x is its own term. Now if I scan this, I see I have a 6, it doesn't have an x. So it can't be a, well, I guess I'm listing like terms. You know what, I take that back. I'm just gonna list the terms for now. I'll come back to that listing like terms. So just listing the terms, 5x is its own term, okay? The next one is 6, so I'm gonna separate this with a comma. There's a 6. And again, I'm just scanning this. So next up is 2x squared. So I'm gonna write 2x squared. Next up, I'm scanning. Some students would say this next term is 9, but it's not just a 9. Remember, every term will take the operation to its left as its sign. It's actually a -9 right there. But it's the operation to its left that becomes its sign, whether it's addition or subtraction. Subtraction makes it negative. Next up, I see the next term is -5x squared. Next, I see a -12x. Then a +4. Then -5x. Again, I'm just scanning this. And once again, this 5x here is negative because of the minus sign right there. So -5x, next up, we got a 3, and it's positive because of the plus sign, 3x squared. And then a 4. Kind of ran out of space there. Then I see I have a 3x. Then a -8. Then a 2x. And then finally, the one at the tail end there, again, it's positive x squared because of the plus sign. That makes it positive. All right, so we did list all the terms. Now I'm going to go into like terms. But again, we've already identified that there's 3 different types of terms. I have x terms. Then we have constants. Then we also have x squared terms. Now again, the x squared there in green that I've listed, that I'm going to be listing, and then the red x, they are not like terms. They're different types of terms because of the exponent of the green x squared. Let's list them. I'm going to start with all my x terms, okay? So once again, let's go back. We know the 5x is an x term. That's nice. Okay, now I'm going to scan this. 6, nope, it doesn't have an x. The 2x does, but it's an x squared, not a like term. -9, no x. How about -5x squared? Well, it's got the x squared again, so that's no good. How about -12x? You could use this list that you made already, but -12x, yep, that one is just a regular x. So it also goes down as another like term with my x's, so -12x. And you can put a comma between there if you want. Continuing to scan this, I got a +4, and then I have this -5x, which is a like term. Then we got a +3x squared, +4, and yep, another x, +3x. And then -8, and then another like term with the x's, +2x. And then the last term there is an x squared, so that's not a like term because of the exponent. Let's go to constants. So I see my first constant there is a 6. That's good. Scanning, we got 2x squared. Nope, that's not constant. It has the variable. Okay, next up we do have the -9 though, which is a constant. It's just a number by itself. -5x squared, no, we use the -12x, but then we see this +4 right there. So we'll list it as a constant. Then we got a +3x squared. Nope, that's not a constant, but the positive 4 is again. We have another positive 4. 3x we used, and then the negative 8 there. Yep, that's also a constant. Then again, we got the x squared at the end. That's not a constant. Now, the rest of these that I have not underlined, I'm trying to keep track of what I've used. They should be the x squareds, right? So let's just double check. Yep, that's a 2x squared, positive, by the way. So I'll list it as my x squareds. Next up, I got a negative 5x squared. Then this positive 3x squared. And then finally, it shows x squared. Just to emphasize the coefficient there is a 1. I'm going to show it. It's a phantom 1, but I'm showing it. All right, so there's my like terms. Now the coefficients here, I'm just going to identify these because it's good practice and it's important for you to know what a coefficient is, so in the future when I say it, you know what I'm talking about. But it has to be with a letter, right? So I'm going to start with my x's. I see that I have a 5x, then a negative 12x. I'm looking at my red list here. Then I got a negative 5x, then a 3x, then a 2x. These red ones are all the coefficients of the x terms. But now I'll list the next ones in green because I'm looking at my x squared terms. These are still coefficients even though they're being multiplied by an x squared. I have a 2, a negative 5, a 3, and again, is where it may be useful to see the 1. It's a 1x squared. So there's my coefficients, all right? So we've identified these, but now it says that we need to simplify. So let's go and do that. Now, usually if I was doing this, I wouldn't list these separately, as fun as that was. I'm going to start with my x terms just because my first term here is an x. And usually I would show it like this. So I'm just going to bring all of my x terms together. And I know they're x's, so I'm going to have an x there ready to go. I'm just going to list the coefficient that goes with it. Now, what I'm going to do as well is I'm going to use the calculator. So I'm going to take this 5, and then I'm going to do minus 12, minus 5, plus 3, plus 2. And that will tell me how many x's I should have in the end here. And when I do that, I get negative 7. So again, if you were to combine all these, you would get negative 7 x's. Now I'm ready to do the constants. So I have a 6 minus 9 plus 4 plus 4 minus 8. And looks like when we do that, we get negative 3 there from the constants. Now, you'll notice when I list this, I'm listing it fairly close to the negative 7x, just so we understand that it is going to create a new expression, a simplified expression. It's still representative of the original expression, it's just smaller because we don't like seeing all that crap. But I'm ready now for my x squared, right? So again, all my green terms here, I'm ready to combine. These will become my new x squared term. So if I were to look at these x squareds, I got 2 minus 5 plus 3 plus 1. And that would give me a total of 1x squared. So I will show it, it's positive 1x squared, so I'm going to show it as plus 1x squared. Some students, though, they don't like to see that 1. They'd like to make it a phantom 1. It really is up to you. It is exactly the same expression, but this is the one we're looking for right there as a simplified expression. Now, what this also means is that if you wanted to, you could take this expression and break it back up into this stuff if for some reason you wanted to and it was helpful. So here's our distributive property. When we see distribution or distributive, it really means multiplying. It strictly is for multiplication, that is all. So if we see that we're going to be distributing, it means that we are going to be multiplying. This example, which is abstract, they're not, usually these would be numbers or terms. Well, it's kind of its own term, but it's showing here A, B. They're not showing the multiply sign, but it is there. So if you wanted to see it, you could put it in there. Same with the A and C right there. It's possible that you may be more familiar with these, with what we call distributive rainbows. Why do they call them that? I don't know, but that's what they call them. So do keep in mind, though, if we were to see something like this, if I were to see something like this, some students know that you multiply, but you can, if you wanted to, call that distribution. And you could even show that green rainbow that I put on there. It is possible also that you may have to distribute between 3 values. So I'm going to do this abstractly again. So we're going to do B, C, and D. So let's distribute that A, right? Well, that means that I'd have to take the A and distribute it to the B. So I'd have A times B, and then another A times C, but you can distribute to a third term. You can distribute to as many as you need to. But, yeah. Distribution is always multiplication, like these ones, okay? So it is multiply, and I'm going to distribute. It is distribution. That's 6 times 3x. So again, this would be a question of how many x's is that? Well, 6 times 3 would be 18. Another way to say that is 6 groups of 3 x's, and you end up with 18 x's. This next one can cause a little confusion because it's m times m. Now, I know I'm going to have 7 of them, but I need to understand what m times m is. If I were to simplify this mathematically, not that I think you do this all the time, but it's preferable to show this as m to the power of 2, m squared. And that would be considered fully simplified. But notice, I didn't need to multiply that m by the 7 because it was already being multiplied by 7. Also, it's not addition, which is a fairly common mistake. Do not add those together. It is that we are multiplying the m's together. All right, well, what about this one? Yeah, no problem. We can still do this one. So it says use the distributive property to write an equivalent expression. No problem. So let's start. I'm going to start by distributing this 3 to the w, and I'm even going to show that phantom 1 there. So that is going to be 3 times 1 w's. 3 groups of 1 w's. How many w's will that be? 3 of them. Now I'm ready to distribute the 3 to the 7 x's, so that'd be 3 groups of 7 x's. How many x's is this? Well, 3 times 7 is 21. It's positive, so I'm going to show a plus sign between there, and that's my final expression. Some students make the unfortunate mistake of combining the 3 w's with the 21 x's. Again, these are not like terms that you can combine, so please do not combine them. All right, well, yeah. Probably as expected, we want to distribute among 3 values, but again, it's no problem. I know I'm going to distribute 9 to the 4a, and distribution is multiplication. 9 times 4a's would give me 36 a's. Now I can distribute the 9 to the 10 b's. Again, I'm going to show this work. Not many students would show this much work right here, historically. But I'm showing it just so we can remember that distribution is multiplication. So again, how many b's? That's a lowercase b, it's not a 6. 9 times 10, it's 90 b's. It's positive, so I'm going to put a plus sign right there. Now this next one, when I distribute the 9, it's a 9 to a negative 7, so I'm going to show it as 9 times negative 7. Okay, why is it negative? It's because the 7 takes the operation to its left as its sign. It's negative 7. So 9 times negative 7 would result in negative 63. But notice I put the negative as a minus sign, and I see now that I have 3 terms in my expression, but they're all like terms. So I know I cannot combine these any further to simplify, and this would be my final expression from the distribution. Now, you may even say that's not necessarily simplified, which could be true, but it asked us to distribute, and that's why we did it. All right, well, this one has subtraction there. How are we going to use subtraction to distribute? Well, again, a common mistake here is where students may take this negative 6x and distribute it here. That's not what you can do. You can't do that because it's being separated by subtraction. And remember, distribution is always multiplication, not subtraction or addition. It's always multiplication. And so students would say, all right, well, what am I distributing here? This is where we got to go back, and we have to know that right here we are distributing a phantom 1. In fact, it's not even just a 1, it's a negative 1 because of the minus sign. So now that I have that, now I know I can distribute a negative 1. First to 6.8 w, so again, that would be 1 times 6.8 w's. So how many w's is that? It's negative 6.8 of them. Okay, how about distributing negative 1? Again, it's negative 1 distributed to negative 5.6. Why is it negative 5.6? Because of the minus sign. Now, again, you can use your calculator here. You're going to get positive, so that's going to be a plus sign, 5.6. then I can see the negative 6x, I'm just going to drop right there. So the last thing I'm going to do here is just check, is there any like terms that I can combine? And there's not. So this one's done. Now these types tend to cause a lot of problems with students on tests and things. You just need to remember that you are distributing a -1 right here. All right, how about simplifying this expression? This one, we don't see any distribution. We're just going to simplify it. But I can see that all three of these terms are C terms. So this means that I should be able to combine all three terms into an individual C term. So I'm just putting the C there so I know that I don't forget to put it on there later. But what are we combining? This is where it may be useful to see that phantom 1 right there in the first term. It's not just C, it's 1C. So what I'm doing here is I'm doing 1, then, well, that's supposed to be 1, and then plus 9. I'm just looking at the coefficients, 1 plus 9, and then minus 5. And this will tell me how many C's total that there are. You can just throw that in the calculator. You should get 5 C's. And that's it. So yeah, you're going to see problems like this one on the assignment. You got rectangular measures 8p plus 6, and the length is p plus 11. It's asking for us to find the perimeter in centimeters of the rectangle. It may be useful to remember that perimeter is the same as taking length and then adding your width, and then just kind of repeating that right there. Some people write this formula a little bit differently. That's completely up to you. But I'm going to write it like this so I can see all 4 sides. So let's go and think about a rectangle right here like this. Okay, now if the length is, it says up there, the length is 8p plus 6. No, that's the width. It says the length is p plus 11. So I'm just going to label this as my length, p plus 11. And then at the top there, at the beginning, it said that the width was 8p plus 6. So I'm gonna show it right here. 8p plus 6, kind of small. Hopefully that's okay. Now for a perimeter, we need all 4 sides. So I know opposite sides of a rectangle are the same. They're gonna match. They're congruent, however you want to say it. So I got 8p plus 6 there on the right and p plus 11 on the bottom. Now that I can see this, or hopefully it helps to see it, I'm ready to actually make a new expression. So instead of length, I'm going to replace it with the measurement that it gave us, which is just p plus 11. Also, it says that the width, so my widths are going to be replaced with 8p plus 6. So I'm going to do that with the rest of these as well. Okay, so I've got my length. I know it's p plus 11. And then I got my width, which is 8p plus 6. And it's perimeter, so we're just going to add all these together. That's what the p is. You could just make it an expression if you wanted to and get rid of the p. But it's going to represent perimeter. Well, we have an expression here. What have we got? 1, 2, 3. We got 8 terms. 2, 4, 6, 8. 8 terms. But there's only 2 different types of terms. We have p terms, and then we have constant terms. So I'm going to start by combining the p's because it's the first term. And again, it may be helpful to see the 1's there. So I have 1p. I'm dealing with p terms, but 1 plus 8 is 9, plus 1 is 10, plus 8. That gives me 18 total p's. Now I'm ready to combine the constants. I have 11 plus 6 plus 11 plus 6. And that should be a total of positive 34. Now some students may reverse the order here, and they may write it as positive 34 plus 18p. It's exactly the same expression. All you've done is change the order. So either one of these would work. So here this one says rewrite in simplest terms, no problem. But I do see some distribution, which is important to notice because that's what we have to start with. And this will be true even when we start solving equations. So I've got this -6 that I've got to distribute into this set of parentheses. I'm going to skip the work because it's stuff that we've seen. I'm starting with a's, right? I got -6 times this -3a's. That's going to be 18 a's. Then I have the -6 times 4 b's. How many b's would that be? It'd be -24 b's. Now I have this 6 to distribute, but it's not just 6, it's -6 again. All right, so I am distributing that negative 6 first to the 1a. Negative 6 times 1a's would be negative 6a's. And then negative 6 groups of negative 2b's would be positive 12b's. And then that negative 7a is just going to drop. So that is the distribution, which now allows me, because I'm only dealing now with addition and subtraction, it allows me to combine any like terms that there are. And I see some. I see there's a's. I got 18 a's minus 6 a's. Oh, I forgot my minus 7 a's as well. When I combine these, how many a's will I have? 5. Now again, in the calculator, you just do 18 minus 7 minus 6, and that would give you 5 as well. Next up, though, we have the b terms. I got negative 24 b's and then 12 b's. How many b's will that be? Be negative 12 b's. Now again, if you were to write this in a different order as negative 12b and then the positive 5a, it still works. They're exactly the same. They're just shown in a different order. That is all. All right, so this one, a little bit different, but process is still the same. We need to distribute. I'll start with the 8 first. So that I'll show the work on this one because it's not too bad. But 8 times 1, I mean, I'll show the 1 there. 8 groups of 1 z's would just give me 8 z's. And then 8 groups of positive 5 would be positive. So there's my plus sign, positive 40, plus 40. Now I'm ready to distribute this 3 also into this set of parentheses. So that'd be 3 groups of 2 z's, which results in positive 6 z's. And then we also have 3 groups of negative 7. Now you'll notice I'm distributing this positive, as this 3 is positive because it's a plus sign there. 3 times negative 7 would be negative 21. So this is my new expression. It's not fully simplified though, so I need to finish by combining the like terms. So I have my 8 z's and my 6 z's, which would result in 14 z's. Then I have also constants, 40 and then minus 21, which gives me positive 19. Now again, there's the other way to write this, but I'm just going to keep this the same. Hopefully that makes sense now. If you wanted to write it as 19 plus 14z, you could. So this one has a decimal in there. I don't really know what that's for, but expect to see some decimals on the assignment as well. But we are ready now to start distributing because there is some distribution. I have negative 3 first times the negative 5x, which would be 15x's. And then also, it's negative 3 times negative 3y's, which would be positive 9y's. Why is that positive? Because a negative times a negative is positive. We also have the distribution. Again, this is a negative 4 that's being distributed. First to the 5x. Negative 4 times 5x's would be 20x's. And then negative 4 groups of negative 7y's would be positive 28y's. And then, yeah, that plus 9y, plus 0.9y would be dropped. We didn't need to distribute with that. It was not affected by any distribution. So just real quick, a common error that students may make is where they distribute this negative 3 also to the positive 0.9y there. Don't do that because it's separated by addition, and distribution is only multiplication. So I'm ready to start combining like terms. I have my x terms, right? 15x's and just negative 20x's. That would result in negative 5x's. And we have all these y's. I got 9y's, 0.9y's, and 28y's, which appears to be positive 37.9 of the y's. And that decimal's okay. Some students get a little unnerved by it, but it's all right to have decimals in your answer. So we're going to rewrite this one also in simplest terms, meaning that we do need some distribution here. We got 5 times 0.4x. Oh, it's giving me 2 x's. You could put 2.0x's if you wanted to, but then we also have 5 times a negative 0.2, which is just a negative 1. So it actually ended up taking all the decimals away, but then we got plus the 9x. And we only have 2 like terms to combine here. That's not bad. 2x's plus 9x's would be 11x's. And then you see this constant. There's no other constants to combine it with, so I'm just going to put this minus 1 here as the negative 1. And that's it. Again, you could write it as negative 1 plus 11x's. That'd be okay. So there's our 2 objectives. Hopefully you feel a lot more comfortable distributing and then combining like terms. If not, then you gotta ask questions.